Hello, in this tutorial I'm going to be reviewing over how to do some basic truss questions or some reaction force questions which we can use on scenarios like a bridge or a beam or anything that is a body being held up by two supports. To start this, firstly we did the previous recording didn't work, so if you're watching this after attending the class you'll notice this is going to have some differences from the last class. To solve these questions, we have to start by reviewing these four main areas. Firstly, we have to identify what supports are in the system, because different supports will handle forces in different ways. We then have to define what equilibrium is, which will describe the state of our system. We are going to put some sort of loads onto our, in this case could be a bridge or a beam, we're going to put some loads on our structure. And so you have to define what the different types of loads we can put on our structure, and then we're going to find a way to solve this using our hand mathematics and a calculator. So we'll start with supports. As you see here on the document on the left, we have an example of some supports. Right, the first type of supports we have is what's called a rolling joint or a rolling support, or so rockers, frictionless surface. When you're writing it in a three-way diagram, it is going to look like a triangle, right, with some sort of rollers underneath it, right, and you're going to give it a little dot over there at the top. How this joint works is if it is connected to a structure, so it could be connected to like a bridge like this, right? This is it is a pin at the top, so this piece of material or metal over here can rotate in 360 degrees about this point, and then this rolling support can also move horizontally because it's like it is on roller skates, but the support cannot move in the vertical direction. If you are roller skating, you can be pushed around, but you're not going to fall through the concrete. So this support over here will only be able to provide a reaction in the vertical in the vertical up or vertical down. All right. The other type of rolling supports you could have a vertical rolling support, which again is going to have the triangle with a dot. And in this case over here, it is only going to be able to provide reaction in this direction. You can even have a rolling support at an angle. So over here, if we have this as an angle and this angle over here is theta, then we can have our reaction forces are only going to apply at the angle theta. So with our rolling supports, we have what is called a 1 degree of freedom. So it is vertical positive, vertical negative counts as the same degree. Or in this case over here, it's only horizontal. And then this over here is at an angle. So these are all rolling. Next we have a pin joint. So these over here are going to look like a triangle, and then they have like these lines at the bottom of it to denote that it's connected to the ground, but it still has the pin thing at the top. So again, it can still connect to like a support or a truss or whatever by that pin joint. So again, it's going to be able to rotate freely around, but because this is connected to the ground, it is able to provide a reaction force in the vertical and the horizontal. So that's one of the a simpler one to understand. It can take it in the vertical and the horizontal. The last form of support we have is called a fixed support. A fixed support usually is denoted as being connected directly to the structure. They might have lines like this. And how a fixed support is work. This is more how a real world support would work. If you were to get a pole and stick it into the ground, or if they're putting in like a sign in on the footpath, they dig a hole, they put in a metal tube, and then they put concrete around it and seal it up. This is going to be like a fixed support. And the previous one is a hinge, a pin joint. Sorry, a pin support. Alright. And this over here is able to provide a reaction in the vertical and the horizontal, but it is also able to provide support in rotation. Right? If you were to pick up a sign, if you were to go find a stop sign, and if you try to rotate that about the axis of the ground, it's not going to rotate. It's going to resist that rotation. So that's why a fixed support can do all three. For stage 5, we only care about these two. But in stage 6 engineering, and we can show examples, they're fixed supports. In the real world, almost all supports are fixed support. Like if you go to an actual bridge, a bridge is usually always connected by a fixed support to the ground. So when we are doing our calculations, we will have to simplify our bridge into these simpler supports. The next case we have is equilibrium. So we have a scenario where we have a bridge. We have a very simple bridge over here. Alright, let's just say, yep, we have a very simple bridge over here. And this bridge, usually, ideally, we do not want this bridge to be falling down. Alright, so this bridge is stationary, which means its acceleration is 0. Because if we have a bridge, if it is not falling down, it is not moving, so its acceleration has to remain 0. It is also not rotating, so its angular acceleration, which I believe is that symbol, its angular acceleration is also 0. Now, you don't have to worry about what this means, just what the symbol means. It just means its rotation, it's not rotating. Your bridge is not rotating. So if your bridge is not rotating and it's not moving up and down, it is in a state we call equilibrium. It is being completely still. So let's see how we can define this case of equilibrium now. Well, we have A, so we're going to refer back to the big formula in engineering, which equals F equals ma. Alright, F equals ma. We have structures in the real world, and so realistically, we cannot have something with a mass of 0, right? So mass is going to be fixed. And if we have a fixed mass and we have an acceleration equal to 0, we have a real number times 0, so F will have to also equal 0. So we can find out that our force has to equal 0. So what does this mean? This means if I had a ball over here and I put a 10 Newton force over here, this ball would not be in equilibrium because it will be accelerating in that direction. According to F equals ma, if this is a 1 kilogram ball, F equals ma, then A is going to equal 10 over 1, so it's going to move at 10 meters per second to the right of my page. But if we also put a 10 Newton force in this direction, the ball is experiencing 10 newtons of force to the right and 10 newtons of force to the left. And we know that if we add up those two forces together, if we do them head to tail, we're going to get from here back to here, we're going to get a total force of 0. So what we're doing up there is we're adding up both the forces and finding out our force is 0. So we can break down the forces we need for this bridge over here by simplifying everything in the vertical and horizontal. So we are going to say the sum of, that's what this E symbol over here means, the sum of all forces in the vertical equals 0. And then we can say the sum of all forces in the horizontal equals 0. So this means if we add up all the vertical forces, which also means if we have a force happening at an angle, right, it's going to also be simplified by its vertical and horizontal components. So we can do that, vertical, horizontal. So we can get all our vertical forces if it equals to 0. Yes. We then also need all our forces in the horizontal equals to 0. Now we have to deal with this rotation thing. Well, if rotational acceleration is, we want it to equal 0, the equivalent in rotation, force equals mass times acceleration, is what we use for translation, as in like for moving. We use moments is what we use to rotate objects. So we're going to say sum of all moments equals 0, because a moment is what we use for rotation. So we have 3 rules over here. As soon as a question tells you something is under equilibrium, they're telling you these 3 cases are true all the time. Your sum of all forces vertical equals 0. Your sum of all forces horizontal equals 0. And your sum of all moments equals 0. And that is your moments anywhere in the scenario that they have described. Now over here, we are starting to look at some real questions on the left. And over here on the right, we have our example of the bridge again. The next thing we are going to do is to identify what loads are on this system. So in our simplest case, we see by the first question they have over here on the top. In the simplest case, we have what is called a point load. So that would be like in the center of the bridge. We have an arrow pointing down, and it is 20 kilonewtons. So this is just a force. So a point load, which is a force, and our force is a vector, which means that for our point load, it is going to have a magnitude plus a direction. This point load over here has a magnitude, so let me draw that down. If this is going to be our load over here of 20 kilonewtons, we have a magnitude is our 20 kilonewtons. Our direction is, this arrow is showing us it's in the vertical direction. We also have, because it is a point load, we have a point of application. So it's got to show you where it's connected to the circuit, or sorry, to the diagram. And we also have a sense by them showing us with the arrow that this case it's vertically going down. You can also have point loads at angles, but it's in a single direction. The next type of load that we have is what we call a uniformly distributed load. Sorry, not a uniform, a distributed load. A distributed load, which is this one over here. So you have a distributed load which looks like then we have a so a distributed load has these elements. It has the force per distance. It has a direction. It has a length, and I think that's it. Oh, and it has a location. So what is a force times distance? This over here is a distributed load. So think of this as like if you have a whole bunch of cars lined up on a bridge, or if you have a beam itself on the bridge, like the bridge itself has weight. So as you have a bar of metal going across the bridge, its weight is going to be distributed along a point. So what this is saying over here by this diagram, this over here is 10 kilonewtons per meter. So for every meter, it's added an extra 10 kilonewtons of force. But it's distributed. This could also be like an aeroplane wing is lifting up through the whole surface, or if you have like a swimming pool on the top of a roof, that load of the swimming pool or the water is distributed along the whole surface. Now we can calculate what the total force in this scenario is. The total force is going to, if it says it is 10 kilonewtons per meter, and I've said here that it's 2 meters, that means it's going to be 10 times 2 equals 20 kilonewtons is going to be the total force. And to help us do our mathematical solving, we can simulate this distributed load as a single direction. So if this is 2 meters, we find the average location, which is going to be 1 meter in. So this will be the same as doing a 1 meter point load down of 20 kilonewtons. Right, 10 times 2 is 20, and its location, if it's 2 meters, the average point is 1 meter in, so it's the same as doing a 1 meter load going down. The last type of load we have is a rotation or a moment load. So in the diagram that we have on the left of the screen, this is the one. Oh, this is the one from the. This is the one in the middle here. We can put a rotation load. If you think of it as a crane or something, perhaps there's a motor that's lifting up a cable. It could have a rotation, or this could be like an aeroplane has its propellers that are spinning, or a fan. It is providing a moment into the circuit. So it is a moment, and so we know moments, the units are Newton meters. Right, or kilonewton meters, or whatever form you want, but it has a magnitude. It has a magnitude, and its unit is in Newton meters. It has a direction, so it's either clockwise or counterclockwise. It has a location. And that's all we really need for the moment. It has its magnitude, direction, and its location. And from that, we're able to solve stuff. And so it could look like this. We have our bridge over here. We could have a moment over here, and it will be like this. And they could say this will be 20 kilonewton meters. And this over here could be 1 meter in. And that's how we have a look with our moment loads. So now let's look at actually solving one of these scenarios. Let's do the very simplest one over here. So I'm just going to draw this as a free body diagram on my own paper. We have a support, we have another support. This one over here has rolling joints, and then we're going to have a connection beam up the top. We have over here, they have AY and we have BY. They look like they are defining this in, instead of vertical and horizontal, they look like they're describing it in X and Y. So that could be the same as saying this could be vertical and this could be horizontal. Then we have some distances. If we go over here, we have 2 meters and 2 meters, and over here we have 20 kilonewtons. So let's start by our checklist. Do we have our supports? We do. We have a fixed joint and a fixed support and a rolling support. Do we have our loads? Yes. The question will tell you that it's in equilibrium. I didn't write down the question, but I'm telling you this is in equilibrium, so we know that our formulas are true. We know that sum of all forces vertical equals 0, sum of all forces horizontal equals 0, and sum of all moments equals 0. And then we have, and we have our load over here in the middle, so we can solve this. So when we're going to solve this question, we know because of our supports, let me get a different pen for this, because we have defined a support, we know this over here is a rolling support, so we know this support is going to provide a force in the vertical direction. The support A is a fixed support, so it is going to provide a support in the vertical and the horizontal direction. So we are going to have to write out our formulas. If we want to say over this, we can say this is reaction. This over here could be force AV, and this over here could be force AH, and this over here could be force BV. So I'm just using force BV, and I'm using that instead of these words over here, just so I can show you a more generic case. And what these questions are going to ask you to solve is they're going to ask you to find the result, find the reaction forces. So it's these three forces over here. So let's start by, we can do these in any order. What we're going to find is as you do our questions, some of these three are going to have multiple unknowns in it, so you're not going to be able to solve it. So but by solving the other ones, we can find the substitutions and put them in. So I'm going to tell you the easiest one to start off with. The easiest one to start off with is force, sum of all forces horizontal. So let's do that. Sum of all forces horizontal equals 0. So now let's add up all the forces in the horizontal. Well, over here, we have force AH, and we're going to choose a direction just to make our life simpler. We'll say to the right is positive. So force AH is in there, and let's look for all our other horizontal forces. We do not have any other horizontal forces in this scenario, so it's just force AH. So 0 equals force AH, well that gives us our first reaction already. We know that force AH has to equal 0. The easiest case. Now let's do sum of all forces vertical equals 0. In this case over here, we're going to add up all our vertical forces, and again we'll say that up is positive. We have force AV, we have whatever value that is, positive. Then we have over here, we have minus 20 kilonewtons, and then we have another vertical force over here, we have force BV, plus force BV. So in this scenario over here, if that equals 0, we have two unknowns in one equation. We can't solve this. Right? But we know that once we solve either one of these, it can work. So what we're going to do is we're going to go to our third equation. We're going to say sum of all moments. Now, sum of all moments is a very general term. It doesn't tell you where sum of all moments equals 0. It's saying moment anywhere in the anywhere in the system is going to equal to 0. I can do a moment about this point over here and it equals 0. I can do a moment about this point over here and it'll equal 0. I can do, in this bridge, I can do a moment about this point over here in the bottom of the page and rotate that, and that would still have to equal 0 for this to be in equilibrium. So what we're going to do is we're going to pick a point that eliminates the most number of forces, basically, to make our life simpler. Now, over here, before we knew that this was 0, if this was at an angle, for example, this force, this would have a horizontal point, a horizontal reaction. So in theory, there could have been two forces here. So if we do sum of all moments about this point A over here, we're going to eliminate force AH and force AV, because our moment formula is moment equals force times distance, and this is our perpendicular distance. So if we are picking a point that our force is going through, its perpendicular distance is going to be equal to 0. So the moment, the change in moment from that force will equal 0. So we're going to do sum of all moments about the point A, where clockwise is positive, equals 0. Because we've defined that via equilibrium. So now let's calculate the moment about point A. Well, force AH and force AV equals 0 because they are where point A is. The next one we have is 20, and that is a positive 20 kilonewtons times the distance there is 2. The next thing we have is we have this force going up, so that's going to be counterclockwise, so minus force BV times, well, its distance from point A is 4, so times 4. If we then, and equals 0, so then if we just solve this out, we're going to get force BV equals 20 kilonewtons times 2 over 4, and this should equal 10 kilonewtons. So now we know what our force VB equals. So now we can sub this, let's just call these, it's going to be simple if I do this. We can now sub this back into equation number 1. Sorry, not back into equation number 2. Where equation number 2 we had 0 equals FAV minus 20 kilonewtons. Why am I drawing that weird? Plus FBV. We know what FBV equals. We know that is going to equal 10 kilonewtons. We know this is going to be 20 kilonewtons. FAV. So now we can say that FAV is going to equal 20 minus 10 kilonewtons. So FAV is going to equal 10 kilonewtons. We have now found all 3 reaction forces in this scenario. We have FAH equals 0, FAV equals 10 kilonewtons, and FBV equals 10 kilonewtons. Next lesson, next tutorial, we're going to produce a list or a procedure to solve these questions. So we can go through like step 1, step 2, step 3, step 4, because when we do these questions, we're going to simplify it so we can skip this part at the start. We can go straight to the moment question. All right, look forward to seeing that happen. Bye-bye.